During 150 years of development, railway signalling has sought the perfection of total fail-safe reliability. From early days, the operation of points and signals were mechanically interlocked to prevent signalmen setting up conflicting movements in error. Later, electrical locking was introduced to ensure that signals could not be cleared while the section ahead was occupied. Finally, the adaptation of the simple track circuit to become an integral part of the signal control operation resulted in the modern multiple-aspect track circuit block. Mechanical and electromechanical interlocking has now given way to computer-controlled, solid-state electronics in the latest installations, such as this one here at London's Liverpool Street. All this means that signalling has virtually reached that goal of fail-safe reliability. The system simply will not permit human error. However, as the whole purpose of the signalling system is to regulate and control the movement of trains, total fail-safe reliability cannot be achieved unless the system is able, in the final resort, to physically retard or stop a moving train. Let's put it another way. The signalman is protected against the consequences of error, as we've already seen, whereas the driver may still fail to respond to indications given. Certainly the AWS goes part of the way, but once its warning indication has been cancelled by the driver, he is still open to distraction, error, or misjudgment. This is where automatic train protection comes in. Let's begin by looking at what it doesn't do. It doesn't in any way automate the train driving function. The driver still drives the train in the normal way, utilising all those human skills, which no automated system can satisfactorily simulate. So what does it do? Well, firstly, it advises indications about signalling, approaching speed restrictions, and the maximum safe speed at which the train may run. If the train is being driven normally, the ATP equipment will do no more than provide the driver with vital in-cab information. The second function is that of warning. If the driver allows the train to run at a speed higher than conditions permit, the equipment will indicate that action is imminently required. Should the driver fail to respond to the warning given, the equipment will then enter its third function, intervention. It is only at this critical point that control is taken away from the driver. It's now time to look at how automatic train protection actually works. Information is transmitted to the train from line-side beacons, which is situated on the approach to each signal, and in other locations, such as on the approach to speed restrictions. A beacon consists of an electrical conductor formed into a loop and laid in the 4-foot way. The loop is supplied with an electrical signal from a line-side transmitter. Loops vary in construction. On the left, we see a short beacon formed from steel tube. On the right, we see a longer beacon, generally known as a track loop, formed from electrical cable. Unless the train is over a beacon or track loop, the train equipment cannot receive messages from the track. Thus, track-to-train communication is intermittent, and signal aspect information may not be updated immediately. That's a problem that we'll come back to later. The data transmitted by the beacons is picked up by an on-train receiver located underneath the driving cab. The encoded information is then transferred to the onboard computer, where it is referenced against train data for length, weight and brake force, as well as speed information from the on-train tachometer. So we can see that the onboard equipment consists of three components: the receiver, the computer and the tachometer. At the heart of the system is the comparison of actual speed against the permitted speed and against speed distance curves. Firstly, let's look at supervision of line speed or maximum train speed. If the train is travelling at the permitted speed, the ATP equipment takes no action other than providing indications. If the train speed exceeds the permitted speed by 3 miles per hour or more, ATP provides a warning. If the train exceeds the permitted speed by 6 miles per hour or more, ATP will intervene by making a brake application. The tolerances of 3 and 6 miles per hour allow the driver to drive confidently up to the permitted speed, knowing that ATP will not interfere. Secondly, Let's look at supervision of train braking to a target, that is, to a reduction in permitted speed ahead. The onboard computer calculates three speed distance curves: the indication curve, the warning curve, and the intervention curve. As we can see from the graphic, a train travelling at or near a maximum permitted speed of 100 miles per hour at A is required to reduce speed to a maximum of 40 miles per hour at B. By referencing the train data to the line-side data, the onboard computer calculates three speed distance curves. The first is the indication curve. The second, the warning curve, commences at the current limit plus 3 miles per hour and terminates at the target limit plus 3 miles per hour. The third, the intervention curve, commences at current limit plus 6 miles per hour and terminates at target speed plus 6 miles per hour. The indication curve is used to determine the indication point, the point on the track at which an indication of the target is first given to the driver. Let's look at the supervision of braking in more detail and plot the actual train speed. Where the train passes the indication point, the driver is advised of the new speed ahead, in this case 40 miles per hour. If our driver brakes the train without crossing the warning curve, the ATP equipment will simply continue to advise. However, should our driver permit the train speed to exceed the warning curve, the ATP equipment will immediately warn that action must be taken. The driver still has full control at this stage. Should the action be insufficient to prevent exceeding the next curve, the intervention curve, the ATP equipment will intervene by making a brake application. The driver will be unable to release this application until the train is brought below the warning curve or reaches the target speed at B. Now let's have a look at how the system works in practice, beginning with the ATP display on the driving desk. At the center is an analog speedometer. In the center of this speedometer is the 3-character display window. This display window indicates the nature of protection being provided by ATP, or gives the reason for a warning or an intervention. Around the circumference of the speedometer, at 5 miles per hour intervals, are the green permitted speed lights. One of these may be lit, as here at 100 miles per hour, to indicate the maximum speed at which the train may be driven. However, if the green light is flashing, as here at 40 miles per hour, it indicates a lower target speed which must not be exceeded at some distance ahead. Outside this ring of green lights is a ring of yellow lights, also at 5 miles per hour intervals, but only up to 50 miles per hour. These are the release speed lights, and one may be lit, as here at 30 miles per hour, instead of a green light on the approach to a signal at danger. Release speeds are used to overcome a problem of intermittent communication. Put simply, the onboard computer may be unaware that a signal, which was previously at danger, has now changed to a proceed aspect. If the computer carried on supervising to 0 speed, the train would have to virtually stop at the signal, even if the aspect had changed to green. The release speed is the speed below which ATP no longer supervises to the warning or intervention curves. The release speed is required only when the train is between beacons, and the computer cannot be updated with the latest signal aspect information. A release speed is not shown if the ATP train equipment is over a track loop. In this case, the onboard computer knows the aspect of the signal. Below the speedometer are 4 illuminated push buttons of different colors. From left to right, they are marked brakes, pass stop signal, shunt, and on. The 2 center push buttons have hinged covers to prevent accidental use. The best way to appreciate the actual operation of the system is to see it working. So let's put ourselves in the driving seat and take a run over a 4-aspect signaled line under full ATP supervision. For simplicity, we'll assume the minimum ATP equipment on the ground, a beacon at each signal. At the moment, we are running under clear signals on a line with a maximum permitted speed of 110 miles per hour. We can see that the permitted speed light at 110 miles per hour is illuminated. The display window is showing 3 equal signs indicating that we have full protection available in an ATP-fitted area. This indication also means that we are not being supervised to stop at a signal at danger. As we approach the next signal, we can see that it's showing double yellow. As we pass the signal, the display window changes to 2 zeros, indicating that we are now being supervised to stop at the next signal but one. A single blip gives audible indication of the change in display. When we reach the indication point for the signal at danger, a further blip sounds and the steady green permitted speed lamp at 110 miles per hour is replaced by a flashing green target speed light at 0 miles per hour. This indicates that the signal at danger is the most restrictive target, more restrictive than any other speed restriction that may be in force. We are now approaching the next signal at single yellow. As we pass the signal, the display window changes to 3 zeros, indicating that we are being supervised to a stop at the next signal. As we approach the next signal, the flashing green target indication at 0 mph goes out and is replaced by a steady yellow release speed light at, in this case, 25 miles per hour. ATP shows this release speed because it doesn't know whether the next signal is still showing red. Remember, the train is still between beacons, so cannot be instantly updated for changes in signal aspect. As we draw up to the signal, it does indeed change to single yellow, so we can continue. But of course we must keep our speed within the 25 miles per hour release speed to avoid warning and intervention. We must also remember that the display of release speed is not an authority to pass the signal. If the aspect had not changed, we would have to stop in the normal way. If we inadvertently went past the signal at danger, ATP would have made an emergency brake application. On passing the signal at single yellow, the onboard computer receives more information from a beacon. ATP now knows that the signal was not at danger and supervises so as to stop at the next signal. Thus the indication in the display window remains at 3 zeros. The yellow release speed light is no longer required and has gone out. However, the train has already passed the indication point for the next target, the signal ahead, and so the flashing green light at 0 mph has reappeared. So far, we have driven the train within the speed requirements of the ATP equipment. We have simply been advised of the circumstances and the display window has shown steady indications. Now let's see what happens if we allow the train to exceed the speed requirements. We now pass the signal showing double yellow. The steady green permitted speed light changes to a flashing target at 0 mph as before, but we make no attempt to brake the train. As soon as our speed crosses the warning curve, the green light goes out, the display window starts flashing, and a warbler sounds continuously. We must now apply full service braking if we are to avoid intervention. When we have brought our speed below the warning curve, the normal indications will return and the warbler will cease to sound. All is well. Now let's look at the extreme case, intervention. We have just passed a double yellow aspect. The display window is indicating a stop at the signal after next, and the 0 target speed is indicated by the flashing green light at 0 miles per hour. The speed crosses the warning curve, the flashing light goes out, the display window flashes, and the warbler sounds. However, we still make no attempt to brake, allowing the speed to cross the intervention curve. At this point, the ATP equipment initiates a full service brake application. The brake push button lights up to advise us that intervention has occurred. This brake application is maintained until the train speed has fallen below the warning curve. When this happens, the normal indications return and the warbler ceases to sound. The brake push button begins flashing to tell us that the brakes may now be released. This is done by depressing the brake push button. We have now regained full control of the train. What we have looked at so far in this brief introduction to ATP is called full supervision. That's to say operation over a line equipped with 3 or 4 aspect signalling, where the ATP covers supervision to each signal as well as to permanent speed restrictions, temporary speed restrictions and emergency speed restrictions. There are 6 further modes of operation. 2 of these are supervisory. Partial supervision, which provides limited protection when the full supervision mode is not available, and shunting, which provides for low-speed movements without train data being entered. Other modes cover equipment self-test, entry of data describing the characteristics of the train, temporary isolating the ATP equipment during special conditions involving propelling, single line or emergency block working, a special failure mode which forces the driver to isolate the equipment. A full explanation of the modes will be given in our next film, Automatic Train Protection, the Driver Training Module. However, one mode deserves special mention now, the data entry mode. Like any computerized system, ATP can only function properly if it is fed accurate data. So here is a new and vital role for the driver, the entering of precisely accurate train data into the onboard computer. Some of you may be concerned that ATP will mean a lessening of the driver's role in terms of skill and responsibility. This is simply not so. ATP should be seen, instead, as the application of modern high technology to assist the driver and give him and his train additional protection against the results of misunderstanding, misjudgment, or error. Where a train is driven normally, within safe parameters, ATP will do no more than keep the driver informed of the vital speed features of the line and the state of the signalling ahead. It should be seen as giving the driver that security that has long been commonplace for signalmen. Driving over ATP-equipped lines may involve some modification of braking technique to avoid, where possible, provoking warning indications or actual intervention. Generally speaking, however, you should find train handling much as before, but with the added security of really comprehensive information on the state of the line ahead. In the near future, 2 pilot installations of ATP will be introduced on the Great Western Main and Chiltern lines. Each line will be supplied by a different manufacturer, so there will be detailed differences in the equipment used, for example the beacons. However, from the driver's point of view, operation and display will be identical. The pilot installations will provide valuable operating experience of ATP on your own particular railway and will give you the opportunity to play your part in the shaping of the national system. The future will see the introduction of comprehensive ATP to all busy trunk routes and busy commuter lines, while secondary lines will have a more selective application covering certain key signals and speed restrictions. All this adds up to some big pluses for our industry, safer operation and higher speeds available with existing signalling. Whether it's intercity, regional, or commuter passenger, or long-haul freight, it all adds up to a great increase in our competitive edge in those 2 areas where we already score heavily, speed and safety. In our first film, Introducing ATP, we looked at the principles of automatic train protection and how the system operates from the driver's point of view. We saw how, when a train is driven normally, the system simply gives the driver visual information concerning the speed features of the line and the state of the signalling ahead. We also examined the protective features of the system, its ability to warn, and if necessary to actually intervene by making a brake application. In this second film, we shall be examining in some detail each of the modes of operation so that you can gain an appreciation of the practical working of automatic train protection. The system is specifically designed to prevent a train from running above a safe speed according to location and prevailing conditions, and to ensure that adequate brake applications are made on the approaches to speed restrictions and to signals at danger. It thus affords protection against collision with another train, or buffer stops, or derailment resulting from driving too fast, misreading signals, misjudging brake applications, confusion over location or routing, and finally passing a signal at danger without authority. Let's begin with the start-up procedure before the train is taken into service. You will need to have the handbrake supplied until after startup is completed, since part of the procedure involves full release of the automatic brake. Once the master switch is moved away from the off position, the ATP equipment will commence the first of two test phases. The first phase is a test of the audible and visual indications. These indications run sequentially, enabling you to check their correct operation and, once completed, the four illuminated push buttons are tested by pressing and releasing in response to messages in the main display window. Finally, you will be asked to check that working pressure is shown on the automatic air brake pipe gauge and to press and release the on push button to confirm this pressure. Phase 2, the ATP self-test, will now commence. The train brake pipe pressure will reduce to 0 and you will be asked to confirm 0 pressure by pressing the on push button. The pressure will now charge to working level and confirmation of working pressure will again be required. Now the train brake pipe pressure will be reduced to full service and you will be asked to confirm service pressure. Finally, working pressure is recharged and, once confirmed, the main display window will show OK. Once the two test phases have been successfully completed, you may press the on push button to access the train data entry mode or the shunt push button to commence shunt hauling operation. It must be stressed that traction power will not be available until testing is complete, the on push button is pressed, and data entry completed, or the shunt push button has been pressed. If the train is to be operated under full ATP protection, the on push button is pressed, the train must be stationary, and the master switch in the neutral position. The on button now flashes indicating that train data entry is required. This data is entered into the system by means of the keypad, used in response to prompts on the data display screen. The train data normally required by the system consists of your personal identification, the driver PIN number, and the train length in number of vehicles. You will then be asked if the train status is standard. That is to say, the maximum permitted train speed is unaltered and no brake on any vehicle has been isolated. If the train status is standard, answer yes. If your answer is no, you will be asked to give the following information: the maximum permitted speed of the train, the PSR category of the train, the TSR category of the train, the braking rate, the service braking delay, and the emergency braking delay. The entered train data will be checked by the system for logic, and if it's found inconsistent, you'll be asked to enter the data again. However, the final responsibility for entering accurate train data rests with you. Many types of train, for example multiple units, have certain fixed characteristics, and in these cases data entry will be simplified. You can review and amend train data at any time, and of course it must be amended when the composition of the train or its braking characteristics are changed in any way. Once train data entry is complete, the on push button ceases flashing and is constantly illuminated. We are now ready to move away. Initially under partial supervision since, up to now, we haven't passed over a track beacon to receive track data. At this stage, during partial supervision, the permitted speed lights are out and the main display window is showing 3 dots. As we reach our first beacon in a fully fitted ATP area, normally on passing the first running signal, the onboard processor receives the first track data transmission. We have now entered full ATP supervision. The green permitted speed light is exhibited, advising us of the maximum permitted speed, and the main display window now shows 3 equal signs, indicating that we have full ATP protection and are not being supervised to a signal at danger. Should we permit the train speed to exceed the maximum permitted speed by 3 miles per hour, the ATP will initiate a warning. The warbler will sound, the permitted speed light will go out, and the main display window changes from 3 equal signs to the numerical value of the speed restriction and commences to flash. We must now reduce our train speed to within the permitted speed. When this is done, the cab indications will return to normal. Should we fail to react to the warning and allow our train speed to exceed the maximum permitted speed by 6 miles per hour, the ATP will initiate intervention. A full service brake application commences, accompanied by the lighting up of the brake's push button. The system will maintain this full service brake application until the train speed has fallen below the maximum permitted speed, after which the warbler will cease to sound and the brake's push button starts to flash, indicating that the brakes may now be released. We release the brake by pressing and releasing the brake's push button. This action will give a complete release, so that if this is not desired, we should first set the brake controller to the required position. The ATP system will always supervise to the most restrictive target speed. Ahead is a permanent speed restriction of 100 miles per hour, but our next signal is showing double yellow. As we pass over the beacon, the main display window changes to 2 zeros, advising us that we're being supervised to stop at the next signal but 1. When we pass the indication point, the green permitted speed light 0 miles per hour commences to flash. This is the target speed at the signal at danger, 0 miles per hour. We are braking in the normal way, so the ATP remains in an advisory mode. If the braking action had been insufficient to bring the train to a stop at the signal at danger, the system would have initiated a warning, then maybe intervention, as we have already seen. The next signal is showing single yellow. On passing the beacon, the main display window changes to 3 zeros, indicating that we are being supervised to a stop at the next signal. The green permitted speed light is still flashing, at 0 miles per hour of course.
If the next signal now clears to a proceed aspect before we reach it, the ATP equipment has no means of being updated, so it still thinks that the signal is at danger and will supervise accordingly. Obviously, this would be unsatisfactory. It would mean that our train must come virtually to a stand at the signal, even if it's now showing a green aspect. This problem of intermittent communication between the track and the train is overcome by the release speed function. As we approach the next signal, the permitted speed light flashing at 0 goes out and is replaced by a yellow release speed lamp. The release speed indicated is the maximum speed at which the train may approach and pass the signal if it is cleared to a proceed aspect. The release speed is calculated by the equipment so as to be able to bring the train safely to a stand in the overlap should the signal be accidentally passed at danger. This release speed indication might be as low as 0 miles per hour, in which case our speed would be limited to a maximum of 3 miles per hour, the release speed plus the warning tolerance. We can see that the signal has cleared to a green aspect. We must now regulate the train speed to within the release speed indicated, in this case 25 miles per hour, until the beacon is passed. Now the ATP equipment is updated. It now knows the aspect shown. The release speed light has gone out. The flashing green permitted speed light 100 miles per hour has appeared, since we have already passed the indication point for the speed restriction immediately ahead. The main display window is now showing 3 equal signs. ATP supervision to buffer stops is essentially the same as that to a signal at danger. Here we are approaching the last signal before entry to a terminus station. The green permitted speed lamp 0 miles per hour is flashing. As we pass the signal, the main display window changes to 3 zeros, indicating in this case that we're being supervised to a stop at the buffer stops ahead. As we approach the buffer stops, the flashing permitted speed lamp 0 miles per hour goes out and is replaced by the yellow release speed lamp 0 miles per hour. The release speed lamp 0 miles per hour is exhibited to enable the train to be drawn right up to the buffer stops and reminds us that there is no overlap. Now let's see what happens if we misread a signal aspect or fail to stop at the signal at danger. The release speed light is again showing 25 miles per hour. We approach the signal at danger but fail to stop. As we reach the signal, the ATP immediately provokes an emergency brake application. This is called the train trip. At the same moment, the warbler sounds, the brakes push button lights up, and the main display window exhibits the flashing indication SPD. We are unable to release the brake until the train has been brought to a stand. At this point, the warbler ceases, the brakes push button flashes, and the main display indication shows a steady SPD. We may now release the brake by depressing the brakes push button and regain control of the train. However, the train may then only be driven under partial supervision and only once authority to proceed has been obtained. For the next 3 minutes, the ATP equipment will limit the maximum speed of the train to 20 miles per hour, and during this time, the main display window will continue to show SPD to remind us that a signal has been passed at danger. There are some very important points to be made here. Firstly, the release speed indication does not give authority to pass the signal at danger. It is simply the ATP equipment telling the driver that if the signal has cleared to a proceed aspect, he may approach and pass at a speed no greater than that shown. Secondly, none of the indications given by ATP in any way relieve the driver of the responsibility to observe signal aspects and control the train accordingly. As an example, let's look at the situation where a signal is replaced to danger in emergency. We are presently running under clear signals. When the next signal is sighted, it has been replaced to danger. This has taken place after we passed the last beacon, so the ATP knows nothing about it. We immediately make an emergency brake application. The ATP, however, will still indicate clear signals until the beacon is actually reached. It is planned to install train data recorders as part of ATP. This equipment will record track-to-train transmissions, power and brake controller settings, and each occasion that ATP warns or intervenes. What if, having brought the train to a stand at a signal at danger, we are authorized to pass the signal in accordance with the rules? If we were to attempt to move the train past the signal, the ATP would initiate the train trip as we have seen. Once authority has been obtained, we press the pass stop signal push button. This action must be done while the train is stationary and within 60 meters of the signal. The pass stop signal push button lights up to advise us that the train trip has been disabled and that the train may now be moved forward. Once the beacon has been passed, the pass stop signal push button commences to flash as a reminder that the signal has been passed at danger. It will continue to flash until the train reaches the next signal. Remember though, when a signal has been passed at danger with authority in an area of full ATP supervision, the system reverts to partial supervision, at least until the next signal is passed. As we have seen, ATP will always supervise to the most restrictive speed, so that when approaching a signal at danger or buffer stops, the target of 0 miles per hour will always be the most restrictive. We are approaching a permanent speed restriction of 40 miles per hour. At the indication point, the permitted speed light changes from, in this case, 90 miles per hour to the target speed of 40 miles per hour and flashes. Just as we saw earlier, if our braking is insufficient to bring the train speed down to the target, a warning will be initiated. In this case, the main display window will exhibit a flashing indication of the target speed, 40 miles per hour, in numerical value, and the green permitted speed light at 40 miles per hour goes out. Once again, failure to respond immediately to the warning will provoke intervention braking. We have now brought our train speed back within the safe braking curve, and the flashing target speed light 40 miles per hour has reappeared. As we reach the commencement of the speed restriction, the green permitted speed light shows a steady indication. Because the ATP knows from the entered train data the length of the train, when the termination of the speed restriction is reached, the new permitted speed will not be exhibited until the rear of the train has passed the termination point. Full supervision by ATP works with 2, 3 or 4 aspect signaling. Where signal sections are short, it will sometimes be necessary to provide an indication for a signal at danger in the rear of the first restrictive signal. The position where this happens is called the ATP sighting point. In 4 aspect signaling, the main display window shows a single 0, indicating that the train is being supervised to a stop at the next signal but 2. In 3 or 2 aspect signaling, the window shows 2 zeros, indicating that the train is being supervised to a stop at the next signal but 1. Remember, this ATP sighting point might be different from the driver's sighting point, the point at which the first cautionary signal is actually seen. Where we encounter flashing yellow aspects on the approach to a high-speed facing junction, where the route is set for the diversion, the ATP will advise of the turnout speed, in this case 70 miles per hour, in the same way as for a permanent speed restriction. The green permitted speed light flashes at 70 miles per hour, the target speed for the diversionary route. However, should the red signal beyond the junction not clear, we should of course be advised of a target 0 for that signal. The transition from full supervision to partial supervision or from partial supervision to full supervision, is made automatically and requires no action on the part of the driver. The indications given by the ATP display in the cab will clearly indicate which mode is operating. If, however, we leave the ATP fitted area while the system is actually warning or intervening, a particular sequence of events takes place to alert us to the end of ATP protection. The warbler sounds, the brakes push button lights up, a full service brake application commences, and the main display window shows the flashing indication end. The brake application is maintained for 10 seconds, after which the main display window shows the steady indication end. The warbler stops, and the brakes push button begins to flash, telling us that the brakes may now be released. The purpose of this 10-second intervention is to draw our attention to the loss of protection afforded by full supervision. When running under partial ATP supervision, we are not provided with ATP signaling data, so the main display window will normally remain at 3 dots and the permitted speed lights are out. If, however, the train is allowed to exceed the maximum permitted train speed, a warning indication will commence, the warbler sounds, and the main display window shows the flashing indication max. We must now respond with a full service brake application to prevent intervention. The use of letters in the main display window rather than numerals makes it clear to the driver that the train is under partial supervision. We have already passed the advance warning indication for a temporary speed restriction. Unlike full supervision, we have received no indication of target speed ahead. However, should the train speed exceed the value of the restriction, a warning will commence, followed if necessary by intervention braking. The main display window will show a flashing indication TSR for a temporary speed restriction. Supervision of temporary speed restrictions in partial supervision areas will depend, of course, on whether the necessary track equipment is available. Where a position light signal is associated with an ATP fitted main aspect, and this position light signal is cleared, we may proceed under partial supervision without operating any push buttons. On passing the beacon, the main display window will show the indication PLS, and the train speed will be supervised to a maximum associated with the movement in question. Should the train speed exceed this maximum, the system will first warn, flashing the indication PLS in the main display window, then intervene in the normal way. If it is necessary to pass a number of signals at danger, for example in the case of single line working or emergency block working, or if the cab from which the train is being driven is not the leading cab, say in the case of assisting in the rear, the ATP equipment must be temporarily isolated. To do this, the train must be stationary and the master switch in the neutral position. The on push button is then pressed for a period of 10 seconds. To confirm temporary isolation, the main display window will show ISO. We must now remember that no ATP protection is available. To restore ATP protection after a period of temporary isolation, the train must, once again, be stationary with the master switch in neutral. The on push button is then pressed and released, after which train data must be confirmed or re-entered using the data entry keypad. An additional protection afforded by ATP in all supervision modes is that against rolling away. Should a train move more than 10 meters or attain a speed of more than 5 miles per hour in a direction opposite to the setting of the master switch, or in either direction if the master switch is in neutral, the system will immediately initiate an emergency brake application. The warbler sounds, the brakes push button lights up, and the main display window shows the indication ROL. We shall be unable to release the brake by pressing the brakes push button until the train is at a stand. Where a traction unit is required for shunting duties, it would obviously be time-consuming and unnecessary to enter train data, especially as this would be constantly changing. To enter the shunting mode, the unit must be stationary and the master switch in the neutral position. The shunt push button is pressed, after which the main display window will show the indication H. The mode will now permit hauling movement supervised to a maximum speed of 20 miles per hour, but in other respects is similar to partial supervision. If it is necessary to pass an ATP-fitted signal at danger, the procedure is the same as we have already seen. Warning and intervention will be initiated if the maximum speed is exceeded, and the train trip will operate if an ATP-fitted signal is passed at danger inadvertently. However, during shunting duties, it may be necessary to propel the train. To do this without provoking the train trip when the leading vehicle enters the section ahead and thus replaces the signal to danger, we must be able to disable the train trip. When in the leading cab of a forward direction movement, this is done by depressing the shunt push button while the train is stationary and the master switch is in the forward position. When in the trailing cab of a reverse direction movement, this is done by depressing the shunt push button while the train is stationary and the master switch is in the reverse position. In both cases, the main display window will then show the indication P. Remember, the propelling function can only be selected when the ATP equipment is already in the shunt mode. Once the propelling function has been selected, ATP will supervise to a maximum speed of 20 miles per hour and will initiate warning and intervention as necessary. The train trip will only be disabled for the propelling movement. To revert to hauling again, we must stop, place the master switch in the neutral position, then press and release the shunt push button. We must now examine faults on the ATP equipment and how these can be dealt with by the driver. ATP faults fall into two groups: recoverable faults and non-recoverable faults. Recoverable faults are those which do not threaten the integrity of the system, for example improper transmission or reception of track data, or a missing or damaged beacon. When a recoverable fault occurs, we are alerted by the warbler, the brakes push button lighting, and a full service brake application commencing. The main display window shows the flashing indication E, followed by the 2-digit fault code. The brake application will be maintained for 10 seconds to give us a chance to adjust to the possible consequences of a reduced level of protection. After this interval, we shall be able to release the brake. A non-recoverable fault is one which does threaten the integrity of the system, for example a fault associated with onboard train data or equipment. Should a non-recoverable fault occur, an emergency brake application will immediately take effect and the main display window will show the indication F, followed by a 2-digit fault code. We will be unable to release the brake and regain control of the train until the ATP equipment has been isolated. We do this using our master key, after which the red ATP isolated indicator lamp on the driving desk will light. Details of the fault, including the fault code, must be recorded on the ATP fault report form and reported.
Let's sum up this session by considering some of the important implications ATP will have in your day-to-day job, train driving. As we said in our first film, the primary objective is to increase safety by providing you with a sound backup system. But that's all it is, just a backup. There is no substitute for your vigilance, anticipation, and train handling skills. Use ATP to assist you, but don't become dependent on it. The responsibility is still yours, the skill in your hands. The protection provided by ATP doesn't cover every eventuality. It may vary in level from one area to another, or be suspended temporarily because of a fault. Because of the intermittent nature of tractor-train communications, ATP cannot assist you with an immediate response to an emergency, such as a signal being replaced to danger. Your driving technique will almost certainly require some modification in order to embrace ATP. Because of the 3 to 6 mile per hour tolerances, you can run confidently up to the maximum permitted speed, but be careful not to provoke warning or intervention. Intervention braking in particular needs to be avoided. It takes control of the train out of your hands. It causes wear and tear on the stock, increasing fuel costs, and inevitably poor timekeeping. Because of the intermittent nature of the tractor-train communication link, the system will sometimes impose constraints more restrictive than you would normally consider necessary. In recognizing this constraint, use the cab display to determine the necessary response. Remember, ATP is doing its job best when it leaves control of the train in your hands. In other words, when it's providing you with information only.